So welcome back to the video. In this video, we'll be solving a question on gravitational fields. This is a really interesting question, so I thought I would put it and just make a video on it quickly. So it's about Salyut 1 was the first Earth orbiting space station. It was built by the Soviet Union and launched into the low Earth orbit 50 years ago. Salyut 1 orbited at an average height above the surface of the Earth of 211 kilometers, and then the mass is given of Salyut 1 and Earth, and the radius of Earth is given to us. A lot of information that's going to be very useful to us. And then it says, a textbook claims that for astronauts, so we have astronauts in Salyut 1, there would be sunrise 16 times every day. Okay, and then it says, assess the validity of this claim. So basically what's happening here is that, let me just draw it out, give me a second. So basically what the question is saying is that this is Earth. And Earth completes one rotation in 24 hours. The question is telling us that in this 24 hours, this Salyut 1 will move around the Earth 16 times. And hence why there would be 16 sunrise. That's basically what it's saying, because a sunrise on Earth is basically Earth rotating 360 degree, and then we have the sunrise because the sun is right over here. Okay, so that's basically what the question is telling us. So we have to show that does the satellite move 16 times or does it not? That's basically what we have to show. Basically, we have to find the time taken for the satellite to move around the Earth. Okay, and that's going to be basically the time period that we have to find out. We can basically find that by saying that the gravitational force is the centripetal force. It's going to be gmm over r square, and then the centripetal force is going to be mr omega square. Then this m is going to cancel out, and then I'm going to get gm over r cube is equals to omega square. And then I'm going to find the omega value. I can further simplify it, but I think this will be a bit easier. I can find that omega value. Okay. So square root g is 6.67 times 10 to the raised power of 11 times. Now I'll just plug in the values. No need to waste time. So while I was going to plug in the distance, I noticed this is something very unique. They gave you the radius of Earth and the distance of the average height above the surface of the Earth. So this entire distance is going to be 211 kilometers, and this distance here is 6.37 times 10 to the raised power of 6. Now, this r here that you have, this r is this entire distance. Okay, so you're going to have to add it up. Okay, so we're just going to add it, and the reason I'm taking this is because this is the radius of the orbit, and it's the distance from the center of this to the center of this. That's why I need that distance. So it's very important you add both of them and use the right distance value. You plug in the distances, you get this as the final formula to get your omega value. So you get the omega value as 1.18 times 10 to the power of minus 3 rad per second. You know that the omega value and the time period is both are related by the formula. Omega is equals to 2 pi by t, and t is 2 pi by omega. So that's going to be t is equals to 2 pi by 1.18 times 10 to the raised power of minus 3. And that's going to give me a value of 5,311.3 seconds as the answer. From the question that one day is going to have 8.64 times 10 to the raised power of 4 seconds. And in this seconds, Earth completes one full rotation and it has one sunrise. So we have to see that how many times will the Salyut 1 move around the Earth. So how many times will the Salyut 1 move around the Earth in 8.64 times 10 to the power of 4 seconds. So I know in 5,311 seconds it's going to move once. So in 8.64 times 10 to the power of 4 seconds, which is one day, how many times will it move? Will this be 16 times? Will it move around the Earth 16 times in one day? Or will it move less than that? So that's what I have to figure out. So when you divide both of them, you get 16.3, which is approximately 16. So yes, there would be 16 sunrises, and the statement is correct. Statement is correct. This part tells us Salyut 1 made almost 3,000 orbits before falling back to Earth. Calculate the change in gravitational potential energy of Salyut 1 as it fell back on Earth. So we know this change in the gravitational potential energy is going to be the mass times the change in the gravitational potential. So what we're going to get here is the change in the GPE is going to be equals to the mass of Salyut times the gravitational constant times the mass of Earth divided by the distance from the Salyut to the Earth when it was orbiting, and then minus the gravitational constant times the mass and times the distance from the Salyut to the Earth when it lands on Earth. So if I draw it, it's going to look something like this. So position 1, then position 2. Let me just put this here. So this, okay? So this here is your R1, and this here is your R2. Okay, so that's what those values are. Now I'm going to plug in all the values. Before that, I'm going to do something here. I have M, then I'm going to take GM common out, right? So I'm going to factorize GM out, and I'm going to get 1 over R1 minus 1 over R2. And that's going to be equals to change in GPE. Now remember, gravitational potential is negative. I've just ignored the negative sign. So if you want to take that into account, sure, but you can just ignore it. Now, if you're a bit lost, we're basically finding the change in potential, the change in gravitational potential from this position to this position. And then we're multiplying it by the mass to get the change in the gravitational potential energy. So if you remember in electric field chapter, we used to do the change in the work done is equals to the charge times the change in potential. That's the same thing here. The change in the gravitational potential energy is equals to the mass times the change in potential. It's just that we're looking at two different things. We're looking at charges and then we're looking at masses. Okay, so that's what we're doing. Now I've plugged in all the values here. So we have the mass of the Salyut, and then we have the gravitational constant, we have the mass of Earth, and then we have the distance R1, which is basically the radius of Earth plus the altitude above the surface of Earth of the Salyut 1, and then subtracting it by the distance from the center of the Earth when the Salyut reaches the surface of Earth, which is basically the radius of Earth. Now if I do all of this calculation, I'm going to get an answer of, so I'm getting an answer of 3.69 times 10 to the raised power of 10 joules. So that's going to be the answer. I do have a negative sign here as well. Okay. And the reason that I have that negative sign is because the gravitational potential here was negative. So our change in potential energy is also negative. And that makes sense as well. And yeah, that's pretty much all for this question. So next question says, Salyut 1 burnt up over the Pacific Ocean as it re-entered the Earth's atmosphere. Explain why Salyut 1 burnt up. So when things are coming near Earth's surface, there's going to be the atmosphere, and all of the atmosphere is there, and what the atmosphere will do, so we have the atmosphere, and it's going to cause a drag force. A drag force is going to be there. So first point you'll get for writing that there's going to be a large drag force, just not just drag, large drag force on the Salyut 1. It's a very important point that you have to write. You get 1 point for that, and the second point you will get is that what's happening is as the satellite falls, so it's going to experience a drag force. Let me just draw an arrow for that to represent that. So it's going to be the drag force. It's falling downwards. This is going to be the drag force, and the drag force will do work. So work is done by the drag force on the Salyut 1. Okay, so what's happening here is our Salyut 1 wants to move down. But our drag force doesn't want that to happen, so it's gonna push, it's gonna give an upward force on the solute 1, and that's gonna transfer energy. Imagine you're falling down and someone keeps pushing you up. So they're transferring their energy onto you to prevent you from falling down. That's basically what's happening. And basically the solute 1 is gonna gain energy. So the solute 1 will gain energy, and because it gains energy, its temperature will increase. That's why it gets burned up. So second point you will get for writing all of this, and the first point you'll get for that. Okay, so remember to be very precise with your wording and always speak in context. You see how many times I've mentioned solute 1 and I've spoken in context. It's very important to get those points from there. So that's going to be the entire question, and that's it for this video.